Welcome to this new video. In this video, we are going to finish the subsection 1.3.2 about recurrence and transience. So we started with this subsection in the last video, and we defined the time of first return to a state I, as well as the number of visits of a state I, capital Ni. Okay, now we will need this result, this lemma, for if you have a Markov chain on a state S and you have two states I and J, then you have this relation between linking the probabilities, the conditional probabilities. So this is the probability that state I will be visited at least n+1 times, given that it starts from J, is the product of the probability that Ti is finite, given that the chain started from J, times the probability of at least n visits, given that we start from I. Now, I'm not going to prove this formula, it's a little bit technical. You can read it in the lecture notes if you like. But I will apply it twice for j equal I. And for j equal I, this is actually, it has a name actually. This is what we call FII. Okay, and this, if this probability is 1 for j equal I, we say that the state is recurrent, and otherwise is transient. Okay, and then I will apply it for j different from I. Okay, so the first result, establish two equivalent conditions equivalent to the recurrence of a state I. So there is an equivalence between saying that state I is recurrent, and with probability 1, the state I will be visited infinitely many times. Okay? And this series, PII to the n, is divergent. Okay? Recall that this is what? This is the probability of going back to I in n steps. Okay? It's important because I need this to prove that recurrence and transience are class properties. Okay, so I will do a circular proof. 1 implies 2, 2 implies 3, 3 implies 1. Using the lemma. 1 implies 2. I apply the lemma with j equal I. And since state I is recurrent, this probability is 1 by definition. So I have actually what? I have a constant. This sequence, small, depending on small n, is constant. So if I call it an, I have an plus 1 equal an minus 1 up to a1. So it's a constant sequence. And it's 1 actually, because this is this is a1. And we prove that the event Ni is at least 1 is exactly the event that Ti is finite, because the state is visited at least once. So all terms are 1 actually for every n, and therefore the probability that Ni is plus infinity, everything is conditional on state I, right? So I can write the event Ni equal plus infinity as the intersection of the events Ni bigger or equal than n for all n, right? Because if Ni is bigger than every number, then it's infinity, and if it's infinity, then it's bigger than any number. But now we know from the probability rules, now this is what? This is actually a decreasing sequence, right? And since we are dealing with probabilities, by a fundamental property of measures, of finite measures, the probability of the intersection is equal to the limit of the probability, which is 1, because it's constant. And that's it. So this implies that 1 implies 2. Now 2 implies 3. We proved earlier that the conditional expectation of Ni is given by this series. So now, what is the expectation, the conditional expectation of this? So what are the possible values of Ni? Ni actually start from 1 to infinity and include infinity. So in the expression of the expectation, so if I go back to the definition of the expectation, so I multiply probability of ni equal n times the probability okay, so but if I include plus infinity, so plus infinity times the probability that ni equal infinity, right, is a part of this expectation, right, because ni can take the value plus infinity. But since you are assuming that this is 1, infinity times 1 is infinity. So the expectation, the conditional expectation of ni is plus infinity. So the series is divergent. This is why the series is important, because it expresses a mathematical expectation. 3 implies 1, we reason by contradiction, and in doing so, actually, we find, in this case, the distribution of an I when it's not finite, when it's not infinite. So suppose that the state I is transient, so Fii is less than 1. So when I apply actually the lemma with j equal I, right, remember that the product was Fii, right? So actually it's a geometric sequence because the next term is a constant times the previous one. So we get a geometric sequence of ratio Fii, right? This is the lemma with j equal I. And therefore, once again, since this is an intersection of a decreasing intersection of events, then the probability that ni equal plus infinity is the limit. Of course, everything is conditional here on state I. It's the limit as we did before. But now there's a difference because now Fii is no longer 1. It tends to 0. If Fii is less than 1, then this quantity tends to 0 at infinity as n tends to infinity. So the probability that ni is plus infinity starting from state I is 0 exactly. Now, on the other hand, as you know from probability rules, ni is an integer, right? So saying that this integer is equal to n means exactly that it's bigger or equal than n and strictly less than n plus 1. So, right? This is the same event because ni cannot take in between values, between two integers. And as you know, this is what? This is the probability of ni is at least n minus the probability that is at least n plus 1, because if you add these two, they are complementary events. Okay, and that's it. So the first term is Fii to the n, and the second one is Fii to the power n plus 1. So factoring by Fii to the n, I get this formula. So if I go back to the series, which is the expectation of ni, as we said, the expectation, the conditional expectation of ni is the values of n multiplied by the probability that ni equal n. We can add plus infinity, but if you add plus infinity, actually you get 0, so it doesn't influence this term because we'll have to multiply 0 by infinity, and 0 by infinity is 0, as you know from measure theory. Okay, and now I replace actually according to what we said, so I get this series. Now, of course, I can put the 1 minus f of I outside, and we are left actually with something related to the geometric series of ratio Fii. If you recall the formula for the geometric series, sigma of Qn equal 1 over 1 minus Q if Q is less than 1, so Q is Fii here. If you differentiate term by term, you'll get the sum of the series nq to the power n minus 1. So this is why you get this Fii here. Okay, so you'll get 1 over 1 minus Q squared. And after simplification, you'll get this result. This is a classical trick in analysis. Okay, so go back to geometric series here. And this is a finite number, so we get a contradiction. Okay, so actually we prove that if state I actually is transient, then we have a formula. This formula is very important because it tells you about the distribution of ni in case it's not infinite. And it has a name, actually. But there is no common acceptance about what do we call it. So actually, some people call it geometric. So ni is a geometric sequence, random variables with parameter fii, because but I don't know which definition you took. But if we interpret the geometric distribution as being the number of success in n trials, so the first success after n trials, if you compute this, you'll find this formula. So if I add 1, I get ni plus 1 equal n plus 1. And what does it mean? What is the interpretation of this probability? It's the probability of let us say n failures followed by 1 success, so vice versa. Okay. So in case if I is transient, then this random variable is plus 1 is a geometric random variable, right, with parameter 1 minus fii. And so if you negate everything, you'll get 3 equivalent conditions to transience. So saying that state I is transient means the same thing as saying that the probability that an I is infinite is 0, starting from state I. And as you observed, in this case, an I, which is finite actually, follows a geometric distribution with parameter 1 minus fii. Of course, they are equivalent because a geometric distribution cannot take the value plus infinity, right? And this series is convergent because it means that the conditional expectation of an I is finite because an I is geometric. Now, as I said before, recurrence and transience are class properties. What does this mean? It means that if I and j communicate are in the same class, if one is recurrent, the second is recurrent. If one is transient, the second is transient. Why this is so? Because of this criterion here. So suppose that I is recurrent. Then this expectation, this conditional expectation, is plus infinity. Now, since I and j communicate, then there is a path from I to j of length r, and a path from j to I of length m. This was our graph theoretic interpretation of the Markov chain. Okay, so when I say that this probability is positive, this means that I can go from I to j by a path on the graph and of length r. Okay. Now, by a corollary of the Kolmogorov-Chapman equations, recall from the beginning of the chapter, we had this inequality. So pjj m plus n plus r, I can split it into 3 terms. And now, when I do the summation over n, these are 2 constants, so I can put them outside. If this series is divergent, and these 2 are positive numbers, so they do not change the convergence or divergence of the series. So this is plus infinity, and therefore this series is divergent. Now, of course, I start the series from m plus r, so I can write this in this way. But the divergence or convergence of the series is not altered if I suppress finitely many terms. So, in conclusion, if this expectation is infinity, then this expectation is infinity. So state j is also recurrent, according to what we said. And the last result in this video is something that you may understand at an intuitive level. The probability of leaving a recurrent class is 0. Okay, well, If you understand it without proof, then don't worry, you can stop the video. If you want a rigorous proof, here's the proof. So suppose that I is recurrent, and let J be a state not in the class of I. We will show that no matter what, there's no path going from state I to state J outside the class. So if initially I'm starting in state I cannot go to any state outside the class, no matter how long is the path. So for every n, Pij to the n is 0. Okay, so there's no path from I to J of any length. So by contradiction, if this is not true, of course here I can put n in small n and n star because I is different from J. So of course Pij to the 0 is 0, of course. So I can put n star here. So now we distinguish between two cases. If also there's no path from J to I, then this means that the system can leave I and never come back. Okay, because if you go from I to J, we don't go back to I anymore. Okay, so I is not recurrent in this case, because I will be visited. If I is recurrent, it will be visited infinitely many times. So this contradicts the recurrence of I. And the negation of this is that there exists M such that PGA to the M is positive, which means that there's a path from J to I. So what do I have here? I have a path from I to J and a path from J to I, but this is a contradiction again because J and I are in different classes. They do not communicate. And that's it. Okay. I didn't finish actually. So this is the last result. Sorry. So a finite Markov chain has at least one recurrent state. Also, this should be clear from our interpretation of Markov chains. But here's a rigorous proof. So first I link the conditional expectation of Ni starting from J to the expectation of Ni starting from Y. Now, I hope you recall from the first course in probability that the expectation of any discrete random variable can be written in this way. Okay, you can improve it if you like. So if you go back to the definition, you apply some tricks, then so this is true for any expectation. In particular, it's true for conditional expectation. So here I start from 1, so I have to. So if I put n plus 1 here, I have to start from 0. So same thing. And now I apply the lemma, which links this probability to the probability of Ni is bigger or equal than n. Okay. Now I can put this constant outside the summation because it's a constant. And now I split this summation into two terms. The term for small n equals 0 and the term starting from 1. Now what's that? And I is an integer valued random variable. So this probability is 1 actually. So I get this relation between the conditional expectation of Ni starting from J and the conditional expectation of Ni starting from I. Okay, this formula could be useful actually. Now, I reason by contradiction. If Ni has no recurrent state, then we know that Ni, so all states are transient, so this expectation is finite, and therefore this is finite. And therefore, the unconditional expectation of Ni is finite, okay? Because the unconditional expectation, as you may check, is the sum of the conditional expectations times the probabilities. Now, we know from measure theory that if the integral of, this is an integral actually, if the integral of a non-negative function is finite, then the function cannot take the value plus infinity with positive probability. So, if you like, the set where Ni is plus infinity, is of measure 0. Okay, and right, and this is in the unconditional probability. So that means that Ni is finite almost everywhere. So it's probability 1. So what does it mean? So it means that for every I, every state I will be visited a finite number of times Ni. Right? But so if you have a finite number of states, then you will have a finite number of visits. But the set of integers is infinite. So we get a contradiction. Okay, so this ends the video, and I will be posting at least 2 videos per week because I will have to finish on time. So I'm asking you to do some extra effort because we'll have to finish on time. Okay, so thank you for your attention. And by the way, I'm planning to do a Zoom session with you by the end of the course. So prepare well your questions. Okay, so see you next time.